Happy Independence Day to all our future doctors and engineers. I am BK Misra, chemistry teacher, and as always, before starting today's class, today's knowledge. Studying is the penance. You'll have to burn, you'll have to endure, you'll have to study. You are the blessing of gurus, you are the breath of Ma, you are the heartbeat of the father. You are the strength of the friends, you are the happiness of the sister, the laughter of the brother. You have to become the pride of the country. You have to become the identity of the tricolor. Don't get tired. Don't be afraid. Don't bow down. The destination is far. You have to achieve it. Study is the penance. You will have to burn. You will have to endure. You will have to study. Now, with this great thought, I would like to start today's lecture, and the topic of our discussion today is nucleophilic substitution reaction. Nucleophilic substitution reaction, simply known as SN reaction. Nucleophilic substitution reaction. Substitution reaction, or simply known as SN reaction. It is a characteristic reaction of alkyl halides alcohols and ethers. For such reaction, a substrate with leaving group is required along with nucleophile. See, as we know, substitution reaction simply means replacement of an atom or group by other atom or group. And if this replacement via nucleophilic attack, it means substitution due to nucleophilic attack is simply considered as nucleophilic substitution. The general representation of such kind of reaction is RL. This is supposed to be substrate with leaving group. L stands for leaving group. A substrate with leaving group is required along with nucleophile. This is incoming nucleophile. Reaction condition, presence of solvent. For leaving group, we must remember either leaving group is more electronegative atom and more electronegative atom containing group. The reason behind that, this have tendency to withdraw electron. And for this, high electronegativity must be required. See, if L is more electronegative atom or more electronegative atom containing group, then L have tendency to withdraw electron. And as we know, leaving group depart, it means leaving group depart with taking their bonding pair of electron. Bonding pair of electron. See, this is a bonding pair of electron. Leaving group more electronegative atom or more electronegative atom containing group. It means leaving group have powerful minus I effect, and minus I effect should be represented with this arrow. This is sigma bond. Negative inductive effect of leaving group. It means leaving group have delta negative charge. R alkyl must have delta positive. Nucleophile, as we know, electron rich. Leaving group is bonded with carbon. R usually stands for alkyl. It means leaving group bonded with carbon. These two electron, this bonding pair of electron are present in bonding molecular orbital. It means this sigma bond, this pair of electron is in bonding molecular orbital. Lower energy atomic orbital, bonding molecular orbital. If this pair of electron is present in bonding molecular orbital, it means alkyl must have empty anti-bonding molecular orbital. This is empty anti-bonding molecular orbital which have higher energy. Nucleophile simply means electron rich. Nucleophile, philic character, it means loving character. It means this have nucleus loving character, positive loving character. So this nucleophile donate its pair of electron to the anti-bonding empty orbital of alkyl. As we know, a bonding molecular orbital contains 2 electrons, anti-bonding molecular orbital contains 2 electrons. In that case, bonding can be cancelled or compensated via anti-bonding molecular orbital, and for this condition bond order should be 0. It means as nucleophile donate its pair of electron to anti-bonding, leaving group try to depart. The representation of this reaction may also be in this way. Delta negative represent leaving group try to depart. This delta negative of a nucleophile represent the nucleophilic attack of nucleophile on alkyl part in its anti-bonding molecular orbital. And it result transition state. As we know, transition state, it means higher energy state, not stable. To get stabilization, it finally depart leaving group, and the outcome of the reaction becomes R nucleophile and the leaving group. See, this is the simple basic representation of SN reaction. Nucleophile, it means incoming group, incoming nucleophile. Substitution due to nucleophilic attack. This is the simple meaning of nucleophilic substitution reaction. See, nucleophilic substitution reaction can proceed by 6 different kinds which have been designated by Ingold. Nucleophilic substitution reaction can proceed via 6 different kinds of SN reaction, and this will be designated by Ingold. Ingold is the scientist who designed SN reaction into 6 kinds. First one is SN2 bimolecular nucleophilic substitution. Second one is SN1 unimolecular SN reaction. Third one is SNI internal SN reaction. Next one is NGP neighboring group participation reaction, and the next one is SNAE nucleophilic substitution via addition elimination. And the last one is this is first one SN2, this is second one SN1, third SNI, 4 NGP, 5 SNAE, and the last sixth is SNEA, nucleophilic substitution via elimination addition. See, fifth and sixth is mean SNAE and SNEA. Both of these are for ARSN reaction. ARSN reaction means aromatic nucleophilic substitution reaction. SNEA we discussed in the mechanism, follow Benzyne mechanism. SNEA nucleophilic substitution proceed via addition elimination. SNAE addition elimination. SNEA elimination addition. Now first of all we discuss the factors on the basis of classification is done. Classification of SN reaction, we have seen here classification of SN reaction. SN reaction can be classified into 6 kinds based on their mechanism, based on the pathway of the reaction. And this classification is based on the fundamental factors and the factors on the basis of which classification is done on the basis of which first of all we discuss the factors on the basis of which classification is done. And the factors is, first one is living ability of living group. Second factor is nucleophilicity of nucleophile. And the third factor is nature of solvent. And the last factor is nature of substrate. These factors discuss or define which kind of mechanism is proceed in a particular reaction. So one by one we discuss here the factors on the basis of classification is done. Classification simply means mechanism, and mechanism, it means what? It means pathway of the reaction. See, first factor on the basis of mechanism is defined is living ability of living group. Living ability of living group. Now, as we know, living group is either more electronegative atom or more electronegative atom containing group. And living group is also known as nucleofuse. Don't get confused. Nucleophile is different, nucleofuse is different. Nucleofuse simply represent living group. A good living group is one which undergo stabilization after the departure. See, one more important factor about living group, weak bases are good living group. It means living group ability is inversely proportional to basicity. Now, we discuss these factors with examples. See, if the question is given in this way, what should be the order of living ability of living group? Order of living ability of living group. See, the living group is given here I minus, Br minus, Cl minus, F minus. Weak bases are good living group. Living group ability is inversely proportional to basicity. On this basis, we define the correct order. See, if we consider Hi, HBr, HCl and HF, as we know, the order of acidic strength is Hi, HBr, HCl and HF. Why this is so? As we know, the size of atomic orbital, fluorine, chlorine, bromine and iodine. Fluorine have 2p atomic orbital, chlorine 3p, bromine 4p, iodine 5p. As the size of atomic orbital increase, bond length increase, bond energy decrease. So Hi gives bond cleavage more easily. Those which gives easy to depart H plus ion, it means much more acidic. So as acidic strength we find Hi is the strongest acid among these. And as we know, strong acid gives weak conjugate base, anions are conjugate base. So basic strength, anions are conjugate base, I, Br, Cl, F. As Hi is the strongest acid, it means I minus is weakest conjugate base. Weak bases are good living group. It means living ability of I minus is much more greater than that of Br minus, than that of Cl minus, than that of F minus. This is also the way in which we discuss or define the order. One another way to discuss or define the order of living ability. See, if the substrate is Ri, Rbr, RCl and Rf. With the same explanation as we discussed just now for HF, HCl, HBr and Hi. See, here R, it means alkyl part. It means carbon is sp2 hybridized, carbon is sp3 hybridized, and carbon bonded with I, and the atomic orbital of carbon is 2p, iodine has 5p bond length, much more large bond energy, much more weaker bond cleavage easily. So this gives easy to depart I minus ion. On this basis, we also discuss the order of living ability. Bond energy of RL bond. L simply means living ability of living group. Bond energy, as we see here, Ri weakest among all, so I minus depart easily. As bond energy lesser, living ability predominate. Now, few more example. As we know, weak bases are good living group. It means if we consider NH3 and NH2 minus, what should be the living ability of group? Definitely, weak bases are good living group. Ammonia is good living group as compared to NH2 minus. Another example, if we consider OH minus and H2O. H2O is better living group as compared to OH minus. If we consider NH3 and water, definitely water is good living group as compared to ammonia. As we know, water is amphoteric. It means basic strength much more less for water as compared to ammonia. As we know, ammonia is a base. Weak bases are good living group. Now, another example, if the group is H2S and H2O, definitely H2S have living ability much more greater than that of H2O. With the two reasons. First reason, H2S is more acidic. More acidic, it means basic strength is weaker. Weak bases are good living group. On this basis, we may find H2S is good living group. Second point of analysis, if we consider the substrate are bonded with SH2, definitely S have positive charge as it have 3 bond, and other case OH2 positive. See, the size of atomic orbital, oxygen is 2p, sulfur is 3p. As the size of atomic orbital is larger, bond length large, bond energy less, bond cleavage easily. So, with this explanation, we also find living ability of H2S is much greater than that of H2O. Now, if we consider large number of anions, in that case, living ability should be considered as a good living group is one which undergo stabilization after the departure. See, if our living group is given in the question, the group is CH3O negative, C6H5O negative, CH3 C double bond O negative. Now, question is, what is the order of living ability of living group? We see here, this is acetate anion. Acetate anion is stabilized much more extent with resonance here, regular resonance, CH3CO negative double bond O. This gives two equivalent stable resonating structure. In case of phenoxide, this may have 5 resonating structure, but this gives unequivalent 5 structure, only 2 equivalent structure. On the basis of resonance, we see here this have 2 equivalent structure, this also have 2 equivalent structure. Equivalent resonating structure stabilize acetate ion with greater extent as compared to phenoxide ion. As we see in this 2 equivalent structure of phenoxide ion, negative charge over oxygen is localized, although in acetate negative charge delocalized over 2 oxygen atom. See, delocalization should be represented in this way. So as acetate ion undergo more stabilization as compared to phenoxide, and in methoxide ion there will be no resonance factor. So methoxide ion is comparatively much less stable as compared to phenoxide. If the anion is stable, living ability increase. So among these, the order of living ability, methoxide must be lesser or weak living group as compared to phenoxide. Phenoxide must be weaker living group as compared to acetate anion. See, now we discuss overall living ability of living group. On the basis of our textbook, the overall order is given. We discuss the overall living ability of living ability of ability of leaving group. See, Rn2 positive diazonium ion. Diazonium ion is considered as very good leaving group, excellent leaving group. The reason behind that, if nucleophilic attack over R alkyl, the leaving group is N2. As N2 is gas, gases are most volatile, easy to escape out. According to Le-Chatelier principle, if one of the product is gases, it escape out, rate of forward reaction dominate. So, if any of the cases, the leaving group is gaseous species, the rate of SN reaction is exceptionally very high. The reason behind that, gases are easy to volatile, escape out, rate of forward reaction predominate on the basis of Le-Chatelier principle. One of the product is depart, rate of reaction predominate. See, after that, alkyl triplet. This is alkyl triplet, simply represented as ROTF. Here the leaving group is triplet anion, and we see here this triplet anion is stabilized via cross conjugation with these two oxygen S double bond O, and ring also stabilized the anion. And the most important thing is that here the presence of CF3 group. If we see this group, this is trifluoromethyl p-toluene group. As we know, the electron withdrawing power of CF3 minus I power of CF3 is much more powerful. So this stabilizes negative charge density with a greater extent. As we know, anion stabilization, rate of reaction predominate. Now after that, alkyl tosylate. After that, alkyl tosylate. Tosylate p-toluene sulfonyl group. Tosylate p-toluene sulfonyl group, and it should be represented as ROTS. See, tosylate anion is also stabilized via cross conjugation with S double bond O, and somehow it also stabilized with the ring. But the stabilization factor is much less than that of triplet. The reason behind this, here the p-toluene group, and in p-toluene group, positive hyperconjugation effect of CS3 repel electron density of a ring as compared to triplet anion. This is alkyl triplet, this is alkyl tosylate. Although somehow due to O minus cross conjugation and presence of ring, this is considered as stable anion, so leaving ability is reasonably good. After that, the leaving ability of the group alkyl brosylate. Same reason, same explanation. Here the leaving group is brosylate anion. In brosylate anion, O minus stabilized via cross conjugation due to presence of ring, somehow stabilization facilitate, but due to presence of Br and lone pair of Br, this have positive resonance. This destabilized anion as compared to triplet and tosylate. But this is considered as good leaving group due to anion stabilization via cross conjugation. Now, after that, the order is alkyl mesylate. This is alkyl mesylate. ROMS. This is alkyl brosylate. Alkyl mesylate, and after that RI, and after that RBr. See, this is the mathematically defined order on the basis of energy concept. After that, ROC double bond O CF3 trifluoromethyl acetate. Here the leaving group is trifluoromethyl acetate anion. We see this negative ion is stabilized via resonance with carbonyl, and again the presence of CF3 group. CF3 have powerful minus I effect, stabilized anion. So this is also considered as reasonably good leaving group. And after that our Cl or F acetate anion. Here the leaving group is acetate anion. Ester leaving group is acetate anion. After that ether, and after that alkane. See, in this order, RH is in last. It means this does not act as a leaving group. The leaving ability of alkoxide is also much more lesser. This is the overall order of leaving ability of leaving group. Now, after that, we discuss the nucleophile and nucleophilicity of nucleophile. Now, the second factor on the basis of mechanism is done is